So as I mentioned, we will spend some time understanding about tensors and what is TensorFlow, and then we'll learn more about tensor. So what I plan to do is, because we have 2 hours, initially I will give introduction to TensorFlow, then we'll talk about tensors, and one example I will show you where typical 3 neurons are there and then weights are getting multiplied into the next layer. One small matrix example. Then we will have a 5 minutes break. I will share the code, which is a notebook, Jupyter notebook file, which you can also run along with me. We will then go through that cell by cell, understand few things about tensors. Okay, so that's the plan for the day. So let us start with initial discussion on what is a TensorFlow and what are tensors. And with an example, we will end, and then we'll go through some definitions and declarations of tensors using TensorFlow. Okay, so we will be using that for using our environment for it. And as I mentioned earlier, I am running it from TensorFlow 2.0 CLS class. The spider launched from there, so we'll all have the same version. I hope you guys have installed it. In case if you have any difficulties, please reach out to me individually. We can solve it. Okay, or I'm sure you guys are more experienced than me. You can help each other also, so no problem. Okay, fine. Now let us start with introduction. Most of the things you may be knowing, I'm not sure. Okay, let me understand whether you guys know already about tensors or TensorFlow, or am I introducing it for the first time? Have you heard of it? Have you, at least someone has covered about these details? No. Okay, then you know the neural networks and other fundamentals, I think. Okay, fine, no issues. Please stop me in case if I overstep and I assume something you know already. In that case, you can stop me always, so that I can slow down a bit to explain you. Okay, fine. Now what I plan to do is, this is the book which I had referred in the beginning of the lecture, the course. I'm coming back to this book now. There is no single book or something which we can refer in this course, because it has everything from hardware to the algorithms. So we will be concentrating on certain things from some books, something from internet. There are a lot of material around, so you can I suggest you read multiple things, multiple books, articles, to learn more about it, because this is a very happening field. If you have a fundamental knowledge of this, and it will be very useful for you to get into the industry. Okay, what are data flow graphs in TensorFlow? And we will learn about nodes and edges, then tensors in particular. Then I will give you a difference between the earlier version, which I mentioned in the last section, that it was 1.0 and we are going to use 2.0 now. And then one example to differentiate between normal matrices that we have seen in NumPy, and how the tensors are different from matrices. Okay, I will try to do my best to explain the difference. It's still not perfect, I would say, but at least you should know that they are not same. Okay, at least don't conclude that no, because it is using NumPy underneath, tensors are the same as matrices. Okay, they are different. So let us try to see what we can learn from this. Okay, now a TensorFlow is a library, of course, with a lot of APIs exposed to the users, and it uses a graph inside to represent the operation that it is performing. That graph is called Dataflow graph. Okay, it is a representation like our program. When we write a program in a high level language, it is internally represented as assembly code. Okay, in terms of if it is a C program, if it is a Java, it is represented as bytecode internally, and then the bytecode is run by JVM, which finally runs on assembly code of the processor to get executed, right? So this is how we talk to the language. We use the language to express what we want to do, and the language has a freedom to use internally different mechanisms to understand what you are saying in the language, right? Similarly, in C, we say something we want to perform, and it internally converts it into assembly language, which CPU can understand and execute, and finally it runs on the CPU. Similarly, the TensorFlow is a kind of a Dataflow graph representation inside Dataflow graph. And we inform the TensorFlow API using the APIs provided by Google that we want to perform these jobs, we want to create such a model, we want this many layers to be created, okay, this many nodes, and we want this to be connected this way. If it is a dense connection, if we say that it's a dense connection, then every node of the previous layer is connected to the next layer. So okay, I don't talk about what is a node. Node is nothing but a neuron or a perceptron. We'll talk about it little more details. Okay, I presume you know from your DNN courses, or even if you don't know internally how it is done, we are going to see everything about this. Okay, inside what is happening, we will see. There is no magic here, but when you see this working, you will feel that it's really a magic. Okay, we will be wondering how it is actually somebody has thought about it and make it work. So I will show you how things work, so that you will be really amazed how this whole thing is working together. So to represent a network, we are using the TensorFlow API. So internally, the TensorFlow library is going to create or maintain a Dataflow graph like this. But whether will it perform in the same way or will it do some optimization is left to the implementation. I will talk about that when I say TensorFlow 1.0 versus 2.0 difference. When I talk about, you will understand that there is a little bit of optimization done in terms of realizing the TensorFlow graph or a Dataflow graph to perform the job that you want the TensorFlow library to do. Okay. Now let us see what are the nodes in the graph. They represent some mathematical operations. It could be a simple addition or a complex operation like a sigmoid function, which you might have heard about, or it could be a rectified linear unit, RLU. We'll learn about these things soon, more about it. So this could be a node. It may perform something on top of this. That is called, see, when some input is given, it could be an n-dimensional array of data which is coming into the node. It could be from one input because this is the input layer, or it could be from many nodes. It could be many inputs coming. Many data is fed from multiple nodes in the higher layer. Whatever may be, it will perform some jobs on what is coming in as an input, and then it may add some bias. We'll see that later. And they will do some transition also. Okay, translation of whatever is coming, and then it will be output as a n-dimensional matrix again, data which is going to the next level. Okay, this is how the data is flowing through the Dataflow graph. So what we do with the TensorFlow, we will mention what kind of this graph we want to build, and we will also mention what is the data which is coming out of this, how is it going to be computed based on the input? What is the relationship between the input and output? We will talk about that. We will mention what needs to be done here, the translation of the inputs to the output. And then when the output is going to the next layer, what weights to be added? We multiplied, not added. Some weights to be added. Oh, sorry, multiplied. I'm saying again. I'm using adding. Now let me explain what are we trying to do. When we say that we want to multiply some weights on the data which is flowing in this line, we can change these weights. Either a small value it could be, or maybe a large value. Now, when the weights value is changed from small to large, what does it mean? We give more importance to the input which is coming from this layer to this layer. By changing the value to a larger if you are multiplying it with larger value, we are enhancing the signal. Okay, but if suppose you don't want the input from here to be having an influence on the output, what we could do, we can multiply this weight, some weight, by suppressing it. We attenuate it. So this signal is getting attenuated, that its impact on the output is less compared to maybe something coming from here. So we are controlling what is getting communicated to the next layer by controlling the values of weights. So this is how you have to understand what exactly the weights mean. And then we also add some bias to the layer, individual node level, to give some more control on what we want to do. So we will do that later on. Okay, I'm just jumping the gun, and then because you might have heard about all this base and weights and all that, so I'm just telling you that. Now the TensorFlow is giving us a mechanism or a way to pass on the data from one node to the other. Okay, that's the purpose of this whole library. So the library includes various functions that help us to implement and explore machine learning algorithm. See, not only implement, we also try to learn more from it and then try to build more and more advanced neural networks using the TensorFlow. So it is being used for not only development, it is also used for research. So both of them use it. Okay, both the team members or both teams who are working on different things use this TensorFlow to implement it. So we know that there are CNN and RNN architectures are also implemented in TensorFlow. So when I say TensorFlow, you have to imagine that it's a library, whole library I'm talking about. But when I say tensor, it's a one individual data which is flowing either between the nodes or maybe coming into the node or getting out of the node. All are tensors. Now, whatever is flowing through the Dataflow graph is a tensor. It is like this in our home. Whatever is the electricity connections, fan and lights and whatever, they all have 230 volt AC, 50 hertz, right? There is no difference. Once you maybe when I put an adapter and then change it to DC voltage, connect to our Raspberry Pi, it becomes different. But all other things, what is in the home electrical connection is only electricity of AC type with a particular frequency with a peak RMS value of 230 volts. Similar to that, the Dataflow graph has only tensor flowing to this. Okay, data structure which is a tensor. Now you can consider tensor as to be a n-dimensional data. Okay. Now one more thing from the NumPy what you learned, you need to remember that we have the same data type, in the sense if you assume the tensor as a maybe a structure of some multi-dimensional array, individual data in that could be of only one data type. Okay, only one data type. You can fix it as integer 8 or integer 16 or float or 32 or 64, whatever it is, but the data type cannot be something here as an integer, something else here is a float. Okay, that's not allowed. So similar to NumPy arrays where you have a D type which is fixed and we cannot change it. Similar, because the TensorFlow itself is implemented on top of NumPy, it brings all those restrictions along with it. So while I mentioned that the tensor is a data type, a data structure, it can have any number of n-dimensional array, but each of those elements in the array of some particular type it has to be. Okay, but there are various types supported. I will talk about it. Remember, keep it in mind that it has to be of one type where during the execution of one particular model. Okay, now that's why I say that a tensor has a static type. That means you cannot say one training I will run it with the float and then next loop I will train this network with some other data type. No, the static data type, but dynamic dimensions. That dimensions that go through could change. Okay, they can be modified based on the need or based on the data that is coming in. Okay, but the type, basic data type, is constant, so that is static. I hope you understand the difference. Another important property of computational graph, I call it as a computational graph or a data flow graph, both are same, is that only objects of tensor type can be passed between the nodes here. Okay, in this only tensors can pass through, like electricity only can pass through our electrical connection at home, the same 230 volts. You can't connect a US voltage here, which will break down all our electric connections. Okay, fine. I hope this basic understanding you have. Now I'm showing you one example of a graph. This is one layer, the another layer. It receives some inputs, we don't care about it. We are only saying that this is the output which is coming from here. Okay, this is the output, though it is shown as an inside. You can imagine that this 2.5 value is given on all the outputs coming from this particular node. Now this 2.5 which is coming out is getting multiplied by -1 here and getting multiplied by 0.8 here, and that is getting multiplied by 0.2 here, so that the weights are different when they finally reach the next node. So this node is giving an output. You can understand that the whole thing is a floating point values because if there is a real number. So what is shown here is the output, and weights are the things which are getting multiplied. And this is a feed forward network because there is no flow of data in the backward direction. Whatever we give is flowing in this one direction. It's called feed forward network from left to right. A data flow graph is secondly a complete TensorFlow computation. It's basically a TensorFlow computation represented as a graph where nodes are operations and the edges are the data flowing between the operations or between the nodes. Normally nodes implement mathematical operations, of course, but also represent a connection to feed in data or a variable or push out results. Okay, when I say only one output is coming, this value is coming out. If there are multiple output, still the same value is coming out on all of them. Okay, so it's not that values which are coming out from the node is different, but you can make a modification to that by multiplying it with some different values. Either you can enhance it or attenuate it by multiplying it with different values. Edges describe the input-output relationship between the nodes. One edge represents a relationship. These data edges exclusively transport tensors. So these connections are meant for transporting the tensor. Okay, what is coming is called as a tensor, and after getting multiplied, what is going in is also a tensor. Okay, nodes are assigned to computational devices. Now another enhancement they have made it is that each node can be assigned to particular hardware. Suppose you have a GPU or a TPU or CPU, doesn't matter. I can actually make the computations that are done by a node to be executed on a particular GPU. GPU also can be multiple engines can be there. It can be executing on one of them. Don't think that GPU means there is only one unit. There can be multiple execution units. So a node can run on a particular execution unit. That means it's a distributed computing is possible. It could be even over network. It need not be in a one single machine. Now you may wonder what is that big thing involved in making it to run on a particular node. The reason is the inputs could be of millions also, because there are networks which are huge in size. That means the inputs may be coming from millions of nodes from the previous layer. So you may have to actually perform this operation on a particular node, because it may be doing a complex arithmetic in the inside a node. Okay, the mathematical computation could be very complex. All operations have a name and represent an abstract computation. For example, it could be a inverse of matrix or multiplication dot product of a matrix, anything it could be. Okay, because what is coming is a n-dimensional data. Okay, remember that individually also it can be n-dimensional, and on top of it we are having a multiple inputs coming, so it's more complex than what you can imagine. Now you understood about data flow graph, I hope. Let me see if there are any questions so far. Okay, no questions. Now let us go forward. Now I have been saying that tensors are flowing between nodes. Now let us see what is tensor. A tensor is a generalization of vectors and matrices of higher dimensions. TensorFlow represents tensors as n-dimensional arrays of base data type. It could be decided based on when you create it. Each element in the tensor has the same data type, as I mentioned, and it is always known. Okay, when you are seeing a tensor, because I say that a tensor is a static data type, you will know what is the data type that you expect at a node from a previous layer. But since I said dynamic dimensions, you may not know the dimensions of what you get. It could be, when I say dimension, you understand, I hope, as a shape. The shape could be different. Okay, on every iteration the shape can be different, but the type will not be different. So the shape, that is the number of dimensions it has and the size of each dimension, might be only partially known, which are dynamic in nature. So that's a little different from typical matrices. Matrices, you decide about the rows and columns and you don't modify it, but whereas tensors have their dynamic dimensions. Okay, most operations produce tensors of fully known shapes if the shapes of their inputs are also fully known. Okay, what I mean by that, if I have a node, I expect some output and I do some operations here, mathematical operation. If I know that the size of the dimensions of the inputs are known, okay, and of course operation is known, then the output dimensions can be predicted. But when you have a partially known dimensions, then output cannot be predicted. Okay, that will also be partially known. Fine. Now what is a rank 0 in tensor? Is a scalar value, only one single scalar value. There is nothing like this, only a single value. Rank 1 is a simple vector. Rank 2 is a matrix, a two-dimensional matrix, which can be accessed like this, and a three-dimensional matrix and n-dimensional matrix. You can continue. Okay, whatever I told you on NumPy, you will see the same thing in tensors also. Tensors are similar to NumPy data types because they run on top of NumPy. Okay, remember why we studied about NumPy is because tensors sit on top of NumPy. Now, what are the basic things? When you say what are the basic properties, its name, what is the name of the tensor, and its basic data type of the tensor, and the shape. So this is known, basic. So TensorFlow documentation uses three notational convention. Okay, to define the shape of a particular tensor, they may use a rank, they may use the same like NumPy shape, okay, or they will call it as a dimension. Okay, so it doesn't matter, they all mean the same thing. What is the dimension of particular tensor, which is dynamic in nature? But other one is a name. The name doesn't change. Okay, only the dynamic shape is dynamic in nature. Name is fixed when you create a variable. I don't know whether any other place where it could be modifying, but as far as I understand, and data type is also fixed for a particular tensor. It is static in nature. I hope this is clear to you. Now, what are the data types supported by tensor? Okay, these are the data types. You have floating point, 32-bit floating point, which is same as our C float. This is same as C double. 8 bits signed integer, 8 bits unsigned integer, both are there. 16-bit signed, 32-bit signed, and 64-bit signed. So remember that there is no unsigned for these values. There are no unsigned. The reason is, you can imagine why is it. So maybe some interviews, I am just coming up with some reasoning for it. See, if you are having a limited number of bits in your embedded system, what you may be interested in is either to have a data which is flowing through the network to have a range of values either from 0 to 255, or maybe you are interested in minus 127 to plus 128. Okay, this is a yes a restricted IoT kind of a devices wherein you may be interested to define your network either with a quantity which is going to be changing from negative to positive, or it's purely positive. You may have two different things. Now you may wonder why I am not having the similar flexibility of having unsigned here, and slash here. The reason is, once you are able to have 16 bits of data, individual data type, you can satisfy unsigned value. Okay, not going into the negative part of it, only keep the positive side of your values. Then maybe you can have 0 to 2 power 15, okay, minus 1. You can have it as a positive value. Okay, so what I'm saying is, internally your data may not be coming into negative at all. It may remain as positive, but you can still use the signed integer. There is no harm. You can still keep positive values only in your signed integer, and then anything below 0 is not a valid number. You can still have it. Okay, so if they have provided only unsigned here, then it's a problem. You cannot have a signed value in an unsigned thing, but you can always have a restricted unsigned numbers in a signed integer. So remember that. That's the reason they didn't go for a different data type here, which will complicate their implementation details also, because they are optimizing it. So that's how it has been decided. Okay, so you can have a variable length byte arrays or a boolean. Okay, these are the basic data types supported by tensor. Now let us come and learn about what is the difference between TensorFlow 1.0 and 2.0. I think it's around 2017 time frame or 19. I don't remember exactly. I think 19 or 17. This came up, and I think it made public to in 2019 2.0. And you may have some networks which are still using 1.0, or most of the books that you see on TensorFlow, they are all little older, so they may be giving you the code which is 1.0 code. Okay, so if you try to run those TensorFlow examples on our thing, you may have a problem. So if you are trying to learn something out of a book which is following Tensor 1.0, I suggest you install Anaconda, a different environment, and then say TensorFlow. If you don't mention TensorFlow equal to 2.0, okay, then it actually defaults to 1.0. Then you can use these examples to learn something. Okay, so it's not that it's completely withdrawn. It is still there. Only thing is, we have decided to use only 2.0 because looking forward, you guys need to be expert in 2.0 than 1.0, which is almost dead now. Okay, So there are many changes to 2.0 to make the users of TF more productive and efficient. So they want us to be more productive. So they removed a lot of redundant APIs from 1.0. They are not supported in 2.0. And one more thing what they have done is they made it the 2.0 which is naturally um, naturally integrates with the Python. Okay, what I mean by naturally integrating with Python means, see, you write a TensorFlow code, okay, using TF plus dot something, and then you will write TensorFlow related functions you will call, and you implement the code. But you are also free to use NumPy here, okay, and because this code is, after all, is whatever training you are performing is finally running on Python interpreter, and then Python interpreter only is calling the TensorFlow library or NumPy library based on what you use. So underneath Python interpreter is anyway running. So you will be interfacing your code, your neural network, by writing some Python code along with the TensorFlow code. Okay, it's not that you will use only pure TensorFlow like a new language. So they wanted the integrated well with the Python runtime environment. Now, because we are studying IoT and we are going to be porting this whatever model we are training, okay, to our embedded environment. Now this model, what we have developed using Python, okay, on Python environment, using TensorFlow, and of course underneath NumPy, we have built a model, and we train the model. Okay, when we train the model, we decide about the weights of individual nodes. Okay, what are the weights and what is the bias we need to give at each node. We decide about all those things in the during the training. Now when we want to do inferencing, training is a laborious, complex job. You can decide to do more iterations to train better, to decide the weights properly, choose the weights properly so that your model behaves properly. But once you fix up the model, when I say fixed up the model means you have fixed up all the data, how many connections needed, how many intermediate hidden layers are needed, how many nodes are needed in the individual hidden layers. You decide about everything. In fact, decide about the data type, decide about the dimensions to the maximum extent. All this you have done now. Now when we port this model to the ESP32 or some IoT devices, they are not powerful enough to run Python interpreter. Okay, Python interpreter is not going to be running inside it because that itself is a complex piece of module which will not be even possible to even include it here because it comes with so many packages and so many things. So what happens when you do a inferencing is the environment is changing. It's not going to be anymore on Python. So the model is only taken in either in some other form like a TinyML or in the actual form like this typical model, and you only use these already existing weights which have been decided to give input and then expect some output. Okay, so when you port the model from the Python world to the IoT world or embedded world or edge devices, we don't carry the Python interpreter along with us. Okay, we don't need a Python interpreter to perform the inferencing on the model that we have built, a neural network that we have built. So when we do that, we normally what we do is we only take the extract out the weights, or we even modify it from float to maybe uint8 or int8 or whatever, and then a reduced model we take it to the edge devices. So what does the 2.0 has done? Okay, when you are running it on training, when you are doing it on training, it is assumed that you are running it on a powerful machine with maybe GPUs or CPUs and TPUs. But when you do only inferencing on edge devices, you are running it on a low power devices with a lower computing capabilities. So in 2.0, what they have done, they have enabled things to make your life of training the neural network easier, faster, and debugging them better. So they have added some features which are called eager execution, which actually mimics the behavior of Python, like an interpreter kind of a behavior. Whereas in 1.0, they were doing some sessions, okay? They were having some sessions and then they say run the session. Then that particular data flow graph is built and then run. It was little laborious and time consuming job, and it was very complex for the developer to write the model and train it. So they made it simple and efficient by bringing in a eager execution. That means they scrap the idea of having sessions and run, which we were following it 1.0 in 2.0. Okay, you can do the same kind of training using some fit functions. Okay, we will talk about it soon, but just I'm giving you a heads up so that you understand what you are going into. So you may, when you are reading some books, maybe try to read something about 2.0 than 1.0, because you may be reading something which is already dead. So a lot of things are removed from 1.0. Manually, we were actually asked to manually stitch this data flow graph in 1.0 and then do a session run on them. These are all some functions, okay, which we were asked to do it in 1.0, which is not there in 2.0 now. It executes it in eagerly fashion. That means like a Python, like an interpreter. It executes one by one line at a time, like an interpreter, like a normal Python function call. Okay, this achieves both performance and portability. Now I am bringing both because performance, in the sense you can execute it then and there and get the results. Portability is because you are removing the dependency of the Python interpreter being there, and we can easily port it to the embedded devices without much of difficulty in the 2.0. This gives TF the power to freely intersperse Python and TF code. Users can take advantage of Python expressiveness, because Python is always good in terms of writing a crisp code. Okay, that's beauty of Python. So expressiveness is the one of the selling points of Python, which you can use it. Okay, at the same time, a TF code, when ported to other platforms, such as, you can also do this porting to different platform, which is for mobile or IoT or whatever, which is efficient. Okay, so 2.0 is, in a nutshell, you can say that because of the eager execution similar to Python, it is performing better in terms of behavior, in usability, and in terms of number of cycles taken, in terms of performance, and the portability is also simpler in 2.0. Okay, that's just in summary. So it executes the platform context without the need for Python interpreter. Now this 2.0 model, you can just run it on without a Python interpreter being there. Okay, so this is little higher level difference between 1.0 and 2.0. There are many differences. There are no global variables which are there in 1.0. There are some more differences which we will go into the details when we really come to learn about it. Okay, right now let us not bother about them. So this is one where how long we are. Okay, fine. Any questions so far? No questions. I hope you guys are there. How many of you are there? Let me see. 9. Things are coming down. Okay, fine. Now let us spend some time on what are tensors and matrices with an example. Suppose we normally define a n by n matrix with a 3 by 3, and matrix multiplication. Okay, let me explain something about matrix. Okay, what is a matrix? Now suppose you have a 3 by 2 and 2 by 5. Now what is happening? We have some 3 rows. 3 rows. Okay, I have to erase it. Okay, gone. Everything is gone. Okay. Now, when you have a 3 by 2 matrix, okay, is multiplied with 2 by 5 matrix, what happens is this is one domain and this is another domain. Domain in the sense the elements which are there in a particular area, in a maybe a real numbers or whatever. We have this 2 is common here, but what we come out here is a 5 elements and there 3 elements. That means any 3 data points here are mapped to some 5 data points here using this multiplication. So is matrix is nothing but a mapping from every data element from one domain to another domain. Okay, there is a mapping between this to this. Okay, one. Okay, one relationship means there is this particular data element will have a mapping on the other domain, which is only one of the elements. It cannot be mapped to 2 elements here. Okay, every data that you have here will be mapped to one element in this domain. So that's about matrix. Now when we are passing matrix across the different layers means we are conveying some information from one domain to the other domain by multiplying, or in terms of matrices we are conveying that information. Okay, now a vector is a matrix with just one row or column. Okay, one row or a column. So there is a bunch of mathematical operation that we can do. Multiplication is one, which division is not possible on it, but you can do a scaling of matrix, transform it. Inverse you can do, because there is no possibility of division of matrices. We do inverse and then multiply matrices. So these are the basic types of matrix operations that we know. Now the basic idea though is a matrix is just a 2-dimensional grid of numbers, whereas a tensor is often thought of as a generalized matrix. Okay, tensor is a generalized matrix. So tensor is a mathematical entity that lives in a structure and interacts with the other mathematical entities. So as I say, tensor is flowing through a particular edge. It will be getting multiplied by or operated upon by some operations here, as well as a weight could be there which is getting multiplied, and then it will get added to all the weights of the different tensors coming in to finally get the tensor out. Okay, it's actually a tensor lives along with the rest of the guys. So you can imagine that it's not a single entity, it's like a society. Okay, each element in a neural network is living in a nearby nodes and nearby connections. So they are living in a society, kind of a part of something. So if one transforms the other entities in the structure in a regular way, then the tensor must obey a related transformation rule. So what I'm saying is, if there is a changes happening to some tensors, other tensors also should get accordingly modified. Okay, if you change the input dimensions of the tensor, the output dimension also should get modified, because it depends on the different tensors. So though it is matrix is used for implementing the tensors live in a society, kind of live with the other tensors. So any changes happening to the other guys will also impact the tensors in that. So you need to apply the transformation rule to them. So there are some differences between a normal matrix and a tensor. So this is the dynamical property of a tensor is the key that distinguishes it from mere matrix. So if it's a team player whose numerical values shift around along with those of its teammates. Okay, I am calling the other tensors in the network as a teammate, and when the transformation is introduced, it affects all of them. So that's why a tensor has a static data type, but it has a dynamic dimensions, because they depend on transformations happening on nearby tensors, thereby they also get modified. Okay, understand it is like in a home environment. If I say that your power given to your home from your EB fluctuates, instead of 230 volt, suddenly it becomes 240 volt, it affects everybody, every build, every machine in the household, right? So it is similar to that. If dimensions change, it impacts the rest of the tensors also, okay, because the same tensors are flowing through the matrix, flowing through the um, network. So I forgot to have a animation there, so let us add it. Okay, so let us see one example before we go and write something. Rank 2 tensor can be represented as a matrix. Rank 2, you can imagine, this is a rank 1, okay. Either I said that it could be one column or one row. Rank 2 is a weight, okay, weights are there. Now let me try to explain this. You have one layer, okay. Imagine the output, this I already showed you. This is the output coming from this node. Though it is shown inside, it is the output coming out of this node, which is expressed as a particular column of matrix 2.5, 4 and 1.2. This is layer 1, okay, L1. Now these two are hidden layers. That's why you see that some input is coming from the other layer. We don't care about how it is coming, what are the values coming, but we know that the final values of these nodes are this. Now they get transferred to the next layer using the weights which are coming. So though arrows are not shown, imagine that they are all flowing in this direction, okay. It's a feed forward network going in from left to right. Now how do you compute the values which need to be output on these nodes? That is what is expressed in a TensorFlow like a matrix, okay. That is what is represented here. So the weights matrix actually captures that information. Now let us see what is a particular row about. Is this about a particular node, or is it about the next node, or is it one row corresponds to a next node, or does it correspond to the one input node? Now you see that -1 is here, 0.4 is here, and 1.5 is here. So this is from different nodes of the layer 1. So this talks about different nodes on layer 1. So let me call this node 1, let me call this a n1, n2, n3, or maybe, okay, I don't know how to name them. So these weights correspond to coming from different nodes of the previous layer, but they all come to one particular node of the second layer. So this, you can say, L2's first node, which they receive these weights. Along with these weights, the tensors are flowing. Now you can easily imagine what this node, L2 node, first node, this is L2 second node, is getting 0.8 and 0.5 and 0.75. So this all correspond to the inputs coming from L1's layer nodes 1, 2, 3, and these are all what it is receiving on L2 node, okay. This is how it is represented. So if you call this is I and this is all J, if you want to know what a particular node is receiving, okay, let me take an example of this node. It is receiving what values? If you want to know, then you have to look at this, because 0.2 minus 0.3 and 1 are the weights it is receiving from, okay. Different inputs are coming with the different values. So you can imagine that this is how this weight matrix are arranged inside. and they get multiplied with the values which are coming out from here. So this is the L1, and if you multiply it, you get these outputs. Okay, so this, I hope you understand this. Layer 1 to layer 2 weights, that's why W1 2, and they are arranged in this way. Now I am going to tell you what is the difference between a matrix and a tensor. Okay, how is it different? Now imagine, what is an activation function? I mentioned that activation function is something which is performed by the node inside based on the input given. What is the mapping between the input and the output is the activation function. Now if you come across this, why is that name is given activation function is, it's similar to our neural network, where they say that in the brain a particular neural network fires. When they say fires, it gives you output. Okay, so a neural network, lots of input it receives, it fires means it gives output um, based on the some constraint put on the node, based on some constraint. That means if this particular value, whatever is coming in as an input, is more than something, then it will output something. Okay, so activation function is something like what should be the output based on the input, and if the input crosses something, it will give something else. If it is below something, it may give some other output. Okay, if it is a binary output, maybe 0 and 1, or if it is a value between 0 to 1, maybe it will be outputting based on the input value. So that is the activation function, and which is given at each level, actually each node. Normally what happens is, whatever activation function you give, okay, activation function is uniform across all the nodes in the particular layer. Now the activation function may be modified also specific to a particular node. You can say that I want to change it. Okay, you may have initially maybe something which is like common across all of them. This is the activation function. Let me explain this. You might have heard about it, RLU, rectified linear unit, wherein when the input is any negative value, it will output as 0. When it is positive value, it will output the same positive value, because it's a slope which is y equal to x kind of a equation. So every value is mapped to the same thing. So input is x, output is y, it is mapped. Okay, one to one mapping. So same positive value will come out as a positive value. So is this a linear function or a non-linear function? If you are from electronics background, you might have seen ID, VD, and then there is a reverse bias diode characteristics. They call diode characteristics as, okay, this 0.7 volts, piecewise linear. Piecewise linear. That means they approximate this part of the curve as a linear, they approximate this as a linear, and this as a linear thing, because it's a straight line. But all of them put together, it's a non-linear function. So similar to this is also piecewise linear, that from here to here it is linear. The changes are linear. Here to here it is linear because it is always 0. So this function, one second. Okay, so this is a nonlinear transformation, which is 0 and below is always 0. Negative values are all suppressed, only positive values are given as it is. So earlier, I suppose if I have all the nodes having the same activation function, they all look the same. But I may decide to change it based on some condition, that this should be mode. Okay, it is 2. If input is 1, output will be 2. it is multiplied by 2. This remains as 1, same as input, but this is suppressed. It is because I told you that we can decide to suppress the inputs because this node may not be performing something. So you want to suppress the output coming from there. So activation function is one method of suppressing all the input coming from to the node and then what is going out of the node. So I can suppress this 1/5 of what was earlier. So if I do this, suppose, what do I do? How do I do it? I can do it by an identity matrix. Earlier it was 1 1 1. Now I am changing it to 2 and 1 and 0.2, and then I multiply the values which have been computed by these nodes based on these inputs. These values remain the same because I assume that this side there is no change, but only here I am changing the activation function to something else, and at the node level I am changing. Then what happens is I am going to transfer that change across everything because now the output is going to be different. What is coming out of them is not no longer 2.5 and 4 and 1.2. It's going to be 5, 4 and 0.24. Now what happens if suppose I don't want this change to be transferred here? I need to do one thing. I can do it by changing the weights, or I can do the other way. Okay, without changing the weights, can I perform something on this outputs which are coming out to suppress the changes that has happened here? Can I do something? Maybe only specific to these nodes. Okay, maybe if they are connected to some other node, I may be allowing it to changes to happen. But if I don't want that changes happening to this particular things, how do I do it? That you can do it by multiplying it with a inverse of whatever changes have happened. So let me explain what I mean by that. Okay, now I am not doing that right now. I'm showing you what will be the impact of these changes on the output coming. Okay, I am not doing any inverse now. These changes have been reflected and the weights remain the same. Okay, I am not changing the weights, but if I change the activation functions of this layer, I am going to see a different values here. Okay, I am going to see a different weights values here because these weights are not modified and this activation function has changed these values. So that is going to be percolated down in my network and it is going to impact these values. Okay, this I'm just showing that effect of changing the activation function at one layer. Now if I change the weights, in the sense I don't change the actual weights but I transform it by doing a multiplication of A inverse. That means this matrix, okay, whatever the new values that I found, if I do a multiplication of that, I will get back the original value. So A inverse is nothing but the original A, okay, activation function. Okay, let me, maybe I am giving a reference to it. You can read that value, read that matrix explanation for understanding better. These are the A matrix, okay, and I do the inverse of that. Whatever change I have done to the activation function, I am nullifying it by multiplying with the A inverse. Okay, A is nothing but this matrix which I have modified it. Okay, and I am doing the A inverse, I am multiplying it to the weights. Now what happens, the effect of changes that I did to the A is gone now. So you get back to the same value which was there originally now also. Even though these changes have happened, I am now modifying the weights using the A inverse. So remember one thing, I am not really changing the weights, but I am doing a transformation on top of the weights. Okay, so what I want to convey here is that you can perform such operations, transformations on tensors, which is not same as matrix. That's why the matrix and tensors are different, because you can perform some transformations to maybe remove some effects of changes that happen in some layer. It could be for different reasons. I'm not going into the details of those where it is useful, but what I'm trying to convey here is you can apply some transformations across the tensors to nullify some changes that has happened in the previous layers. Okay, so that's the summary of what I wanted to tell you today. Okay, I think we are almost on time. I will give some 10 minutes break. I'm sure many of you are using the notebook already. So just to give you a overview, this basically to enable us to run different parts of the code either individually or as a group. Each cells, you can see that you can run a selected cells or you can run all cells. What happens is a program and all the variables which are declared here are visible to the other cells also. So it's like a single piece of code. You can either run them all, or when you are modifying a part of the code, maybe in the end, you can keep executing it individually. And it also has a flexibility to run this from a web-based thing. It's like a client-server mechanism wherein you can like a collab kind of an environment where you can have the editor front end to write the code, and then the backend server will be executing this like this code what you write. So that is called a kernel, or a particular version of the Python is running in the background. So this is a flexibility that they have given you. Now we have integrated that with the spider, so we will not be seeing the output like what we do on when you run a Python code from the editor. It will not be showing up here, so it will be showing up individually here. So let us run individually. And what we have done, we have imported TensorFlow, NumPy. I have done this also here, but actually I'm not going to be using any of these two things in this program, but we'll default we can always copy here. And one more thing, I'm sure you are aware of it. Control C you need to do for copying, and Control V it doesn't, or you can do this copying, but there is no paste mechanism. Right click is not there. That's one thing. Now let us see what are the constants. How do you define in TensorFlow? Internally, it is using the NumPy, and we have three rows and two columns in dimension. The shape, if you want to know, you can just, I don't know what is the shortcut for this. Run selected cell is Shift Enter. Okay, yeah, I forgot. So Shift Enter. Okay, so 3 rows, 2 columns shape, you can get it. And then print values, it is internally printing it. When you print it, it gives you, as I mentioned, it has got a shape is associated with each tensor, and the actual value of the tensor, which is maintained as a NumPy array internally, and the type is fixed. Based on the value what you are given, it's like a NumPy array initialization only. Only thing is we are having it on the creating it as a tensor here. So the type of this is a tensor. So it gives you 3 values, right? So shape is 3/2. It's similar to what we saw in the NumPy. You can initialize it, and this is a list with one element to say that it's a single vector, a dimension of 1 dimension, and float 32. Default 3.0 is float. Sorry, if you give just a point, it will be float, not a double or a 64. There is no double here. Float 64. This is same. I am sure you doesn't have to be more time is spent here. If it is anything specific, I will talk about it. Otherwise, we can just run once and then see whether we understand what is happening. So we can extract out the shape of the original thing. So suppose if it is 3-2, shape of 0 is the first dimension and shape of 1 is the second dimension. So we can extract out the shape from one type. Okay, val constant, you can see val constant, where was it? This is the val constant. It has a shape of 3, 2. So I am extracting out shape of 0 means the first dimension, which is 3. Okay. That shape of 0 is given, and we are creating a new TensorFlow here. Okay. And we are initializing it with ones, all ones. So the dimension of that is going to be 3, but it will create a new tensor with the values initialized to 1.0. Now what is the type it is deciding? Based on the, let me see what is the, how does it decide the type here. So val constant was integer, but when you give no type here, see what we have done is we have taken the information that I want to build a vector of 3. Okay, 3, a dimension of 3 elements, a single dimension with 3 elements. And so the val constant was used only to extract out the shape of the first dimension, which happens to be 3 element. And when you create it with ones, it defaults to float. Okay, so it creates a float type. Though the original val constant was an integer, it is creating a float type. Only thing is we are using the shape from there. But if you are using the second dimensions shape, then you get 2 element, because it was a 3 by 2. So you get 2 element. It's also float. Or you can create the same type, the same shape, 3 by 2. You can also do that. Okay. Let me execute it. So same 3 by 2. One thing is TensorFlow does not pass on the references to the previous element, what you are giving it as an input to it. Here we are giving val constant shape as an input. We are not using the value stored in the val constant. We are only using the shape of that val constant tensor to construct another new tensor with the values of ones. So that's what is happening. Even the type is defaulted to float 32, not the original type of integer which the val constant is built with. Okay, fine. Now what does it mean? As I mentioned, the static type of tensor is guaranteed here. When you create a tensor, you are creating a new tensor there with a new type. Okay, you are only using the shape to decide about what is the shape of the tensor you are creating, but we are not having a multiple references to the same tensor. We are creating a new tensor. So that's what it means. Now what is the type here? Int32, because this is val constant d type. Okay, we can I should have printed it there. Maybe I should move it. It's out of place. Let me, I'm not able to move it beyond this. Okay, so let me move it here. Okay, so just if you want to type, get a type of the val constant, you can type it. That's all. Okay, nothing much about it. Now let me talk about this particular cell. What is happening? We are creating constants of a particular constant, this value of float type, val float, val int, and what I am doing is val int, I am creating it by casting it. So is it like a typecast that we have in C? Here also there is a typecast. So what happens is it is creating a new tensor. Okay, it is not a reference to the previous tensor, because you know the previous tensor is having a float value. This tensor is having a integer value, so they cannot be a reference. So it is creating a new type. When you pass the value, you are, whatever float value you are given, you are giving it as for creating the integer. Now am I printing the value? Yes, I am printing the type. Now you can see that 3.12 is stored as an integer as 3. So the shape is same. Okay, because it's a constant scalar type. So this list is empty. Shape list is empty because not even a single dimension is a 0 dimension, rank 0, a scalar value. but this is of type float and this is a constant scalar value of type integer. Extracted from this floating value, this integer is created. Okay, so typecast is creating a new tensor from the previous one. Okay, I hope this is clear. Now some mathematical functions that you can operate on the tensor. You create a constant and x is that value, and you can do a square root of that. You can create it. Okay, both are the same type. Okay, so tensor has a lot of built-in mathematical functions which you can use. I'm just giving you a few flavor of what all you can do with tensors. You have a and b constant, so variable is different. Okay, it's just a constant. That means you cannot modify that value. So you may have to, if you're squaring it, you will be creating a new tensor here. Okay, square root of x. Okay, it's a new type. Okay, now what are you doing? Two constants you have, you are adding two tensors here and creating a new tensor here. Okay, tensor add. Because you cannot modify the values of these tensors, it creates a new tensor add, and it is nothing but element by element addition. Okay, so this is clear, I hope. And you can multiply, you can tensors, you can multiply again, because you are creating it from a constant, you are creating a new tensor here. Now how to create a variable in tensor? So constant is this, what you can do with a single value. You can use a constant value, either you can use a raw values here, or I have created a constant tensor with this dimension and the particular values. I can create a variable of that type. Okay, so using the constant as an input, so what happens is the same values get created, but it's a new tensor altogether, and its type is variable. Okay, you can see that it, if you print it, where is this coming from? Yeah, when you print a variable, it prints not only the value, it also prints the type of that particular tensor variable. Okay, whether it is a variable or not. Okay, and anything else you can see here, d type, and is a numpy value. Okay, internally you can see that it's a numpy array. A tensor is nothing but a numpy array of the type. D type is one, shape is another parameter for the tensor. That's it. Okay, I hope this is clear. Now let us print the shape of this variable, type of the variable, and the numpy values in it. Okay, internally. So here what you start is happening is actually it is converting from tensor to numpy. Okay, when you do tensor variable which is a tensor, and numpy when you do, it's like a typecast. When you typecast from float to integer, you are creating an integer. Here you are creating a numpy array from the tensor. Okay, actually you can exchange between tensor and numpy very easily. Okay, because they are internally represented as using the numpy library package. You can actually exchange between or change between a tensor to numpy very easily. Okay, so you can get as numpy, you can get it. Okay, it is a numpy value. Okay, you don't think that internally there is something else numpy is there, but it's like creating a numpy to tensor conversion. Okay, now you can also create variables of false boolean type or a complex number. Only thing is, in engineering we do I a comma ij or ib or j comma j will be putting it before, but here they put it afterwards. Otherwise it's a variable type, and then the shape and the complex 128 type. You know that 128 means 64 plus 64, so complex numbers are double, internally float that 64, and that's why it's called complex 28. Okay, you know that. Okay, here what is happening, we are having a variable a, and then when you create a new variable b based on the value a, it's not same as what you see in Python. In Python, if you say a is a variable and then b equal to a, if you do, it actually passes the same reference to b. it it still refers to the same object, right? We say that it's only a label and it has the reference to the original variable, whereas here it actually is like a constructor. It creates a new variable b, new memory is allocated, is a totally two different values based on the input a. Okay, so how will I demonstrate it? A is initially created with a single vector with the values 1 and 3. Now what I do, A assign. I do a, because it's a variable, I can assign some other different number. It's not a constant. So 2, I am changing it to 5 and 6. Okay. And then I am printing A and B by converting into numpy and then printing it. What I get? A I get, I am printing this, which is A is 5 and 6. Now you see the difference here. Originally this variable was created with the float type because 2.0 and 3.0 was given. And then when I am initializing it, I am giving an integer value here. But still I get a float here. That means that static type which I mentioned is preserved. The type of the original variable A is preserved even though I give input as integer. It converts, it promotes the integer to float and then saves the value in float. So original static type is not changed, but the value is changed because it's a variable. It's a tensor with a variable. It's a variable of tensor type. Okay. So A is printing 5 and 6, but not 5 and 6. It prints 5.0 and 6.0. B originally was having this value, so it remains the same. So it clearly says that A and B are two different locations in the memory. They are not the same like what you normally see in Python. So tensors, when you assign or when you create a new variable, it actually creates a new one. It doesn't pass on the same reference of A to B. Okay, that you should remember. And then what you do, you are performing some arithmetic operation on A. So individually 5 and 6 are added to 2 and 3, which becomes 7 and 9. And subtracting the 7 and 9 from A gives you 0 back. Okay, all zeros. So here the A remains the same, but the value changes and the type remains the same, float. I hope this is clear what is happening here. Because you are doing this numpy only to extract out the values. Okay, otherwise what will happen is when you are printing it as a TF, it will print all the nonsense. Okay, sorry to say that, but all the things about the tensor. It says what is the shape, what is the type, what is the numpy inside implementation. It shows everything about the tensor. So if you want to print only the value, if you are interested only in the value, you have to extract out the numpy portion of it and then print it. That's what is happening here. We are just interested in the value which is getting changed. So if you don't do this, it will print all the information about the tensor. So we are doing it by extracting out the numpy portion. Okay, so I hope this is clear. Now let us see what is happening here. My tensor, I am taking something from previous cells, and then I am creating a variable of type A with the my tensor as the reference or a base based on the original tensor, which is my tensor. But I'm changing the name here. I'm assigning some name to it. As I mentioned it, shape is one parameter of a tensor, name is one, okay, and the type is one. These are the three things each tensor has. So I am assigning a name now with the mark, creating a tensor A. Now A is the label or a reference of the tensor. Okay, this is different from the name of the tensor. This A is different from the name of the tensor. So this object is a tensor object, but the tensor itself has a name built into it apart from the type and shape. So I can create two variables of two different tensors, okay, maybe with different values, but same name. I can have a same name of a tensor, but they can have two instances. Okay, this is very important to understand and remember. Okay, now when you look at this plus one, it's like broadcasting that we learned in NumPy. So whatever is the shape of this my tensor, this one is added, this scalar one is added to all the elements of that my tensor, and those values are passed on to create a tensor variable of that shape, and a name is assigned as mark only. So A, B are two instances of two different tensors having the same name. If you say if they are equal or not, they are not equal, so you are likely to get a false as an output. So let us see the output now. My tensor is originally, if I print just a my tensor, I will get whole lot of information about it. That's why if you are interested in only value, you will say dot numpy, then you will only get the value. Otherwise, you will be getting all the other additional information about the tensor. So that's what is the original input that we have. My tensor is value having 1, 2, 3, 4. Now we are creating a variable of A, and then I am printing A. When I print a tensor variable, it has two different entities coming out. One is about the variable information about it, and then the numpy and the float. So the complete information is coming. It is of variable type of tensor, and its name is mark, which we are given. Maybe we should say give some Indian name. Shape is 2 by 2 because we originally gave my tensor as an input to it. So it has taken the shape from there, values from there, and it has added the name here, and then created a variable of type whatever is the original type of the my tensor. So it was float, and it is also float here. Okay, this is float originally, so this also created a same type. So it is taking the information about the shape, actual value, and the type from the original tensor that we have passed on, and then name it adds tags to that. So it is adding the name to it. Now see, the variable B is also having the same name mark, but different things are all same, and this value is different because we have added a plus one here, which is a broadcasting feature. So it has added 1 to all the values, so 2, 3, and 4, 5, and this is what you get, B. Now when you try to see whether A and B are same, this is a okay, it is not like our Boolean comparison. It is creating a new tensor here. Okay, this we studied, or we realized it at, I think, in the last class of NumPy, that when you do this, it's like a broadcasting feature, and this Boolean operation of equal to is performed on all the elements of A and B and passes out a tensor object of the same type, same thing. Okay, so you get a tensor with this false, 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 because individual elements are all different, and the shape is the same as the original shape, and the type is Boolean. So that's what we get. We don't get a single value like a C comparison. So I hope this gave you some introduction about how a variable is defined, how constants are defined, how different operations are performed on tensor, and how tensors are having different names, can have same name but two different tensors, and broadcasting feature works on tensor also, like NumPy. Whole lot of things we learned. Okay, I hope everything is clear. Then we can break. Tell me if you have any doubts, otherwise we can say bye bye for this week. Anybody having any issues in installing this reference environment on your Anaconda? I hope so. All of you are having it? Oh, sorry. No, sir. Clear. Okay. One more thing, guys. Can you please explain again? After passing integer value to a, it becomes float data type. Okay. Where am I? That I think we saw it in once, right? Okay. Let me see. Here. Okay. See, this is a feature. Okay. I am not saying it's a bug or anything. So let us study what is happening. TF1s is creating a tensor which are initialized with all ones, and it takes the shape of the input tensor given. Now what is val constant? Val constant is of shape 3 by 2, but its d type is integer. We know that because we saw val constant d type is also in 32. Okay, we were sure about it. Now we did that. Okay, let me go to this one, the intermediate one, but all of them behave the same way, all of them getting float. Now when you say shape, it only takes the shape information from the original tensor, and then when you say once, it is you are initializing it once. Now you have an option whether you want this once to be either an integer or a float. So this function, which is initializing the tensors on creation with value 1, has a default type d type given as a float 32. Okay, internally the default is given as a float 32. Since we are not giving any information about what type of tensor we are interested in making, we are only giving the shape here. It only takes a shape and then creates it with the float 32. So let me change it with d type. I'm sure it is correct. Let me see. Okay, I'm not sure whether it will work or not. I think we have to give it here. No. Let me see in once. What do I have to give another parameter to this, or okay, somebody has typed if TF1s will always create tensor of float type only. We just provided shape here. Is it so? Okay. No, what if we want to create a integer type? Shouldn't
can you try it once as string?
Sorry. No, this is the correct usage, right?
Sir, int 32 as string.
Oh, is it so? Correct. I think previously also this came. Let me see. You are right. Very good. Thank you. So, okay. Who asked the question? Sandeep. No, Tanmay asked the question. Mayank cleared the doubt. Okay. So, Tanmay, do you understand, Tanmay, that if I don't give this, the default value is set internally for this once function as a float 32. That's why it is creating a float 32 type, okay, on creation. But if you specifically say int 32, then it will do the int 32 type, okay. But shape is taken already. So it is nothing but our default parameter that we learned in Python, okay. That's the beauty, okay, learning Python and then NumPy and coming here, you are already ready to digest TensorFlow. Tensor as well as TensorFlow. Okay, good question. Okay, you understood. Very good. Okay.